Okay, thank you very much. I'm very happy to be here. Okay, so this is joint work that's 2 papers with 2 different sets of co-authors. One set, which is the majority of the talk, is Michael Shapira and Robert Leitchev, who was my visiting student for 2 years. And then a bunch of other students and my colleague Leo Raisin on the remaining 2 works that I'm going to talk about. Okay, so what is the purpose of this talk? There has been a lot of activity to secure BGP, to secure routing, and there are various proposals that are in place. Today we're in a situation where things are actually being deployed. There are 2 solutions that are being looked at. One of them is sort of step 1 and the other one is step 2. And what this work is about is how important is it for us to get to step 2. Okay, so I'm going to analyze both of the solutions, talk about what step 2 gives us over step 1, and then what are the challenges of deploying step 1. So those are the two questions. Okay, so earlier in the morning we had a talk about autonomous systems in the AS level topology, but some of you weren't here, so I'll just review quickly. So what we're interested in is routing between autonomous systems, between giant networks in the internet. Each one of these is a giant network run by a particular organization. We call them autonomous systems. Chaya talked a little bit about the attack on Spamhaus. So this particular part of the topology here, this is Spamhaus server that was hosted at this autonomous system. And if you wanted to reach this autonomous system, the way you would do it is, this is the IP address of the Spamhaus server. This thing down here is the prefix that this IP address is contained in. So just as a quick review, I know this is a networking session. This is a /24 address, which means the first 24 bits are fixed and the remaining are free. So all addresses contained within this prefix with any suffix is a /24. So I'm going to need this notation all through the talk, so pay attention. /24 means the first 24 bits are fixed. So if you want to reach this /24, the way you do it is you do it using BGP with routing. So what happens is this autonomous system will send out a message saying, if you want to reach this /24, you go through me. And then this process continues. Each one of these networks will send out an announcement with the entire path from themselves all the way down to this autonomous system, which we call the origin, that has this /24. Okay? So that's routing with BGP. And what I'm showing here is finally this network in the Netherlands learns the route to the /24, and it's going to select the route. All right, so in March, there was an attack on Spamhaus. The attacker was called Cyberbunker. This was a denial of service attack, and Chaya talked about that a little bit. I'm not going to talk about the denial of service attack. There were many different things that this attacker did. One of the things he did was a BGP attack. Let me show you exactly what he did. This is a different part of the attack. So some of you may have heard of the denial of service parts. This is different. So here's what he did. This network here set up a server here that was going to masquerade as the Spamhaus server. Okay? And what this network did in BGP was it announced that it was having a path to this IP address. So this IP address here is a /32. So what does that mean? It's a single IP address. That single IP address is the IP address of this server here. Okay? So now, how does routing work in BGP? This network here, greenhost, has 2 different addresses that it can choose from. It has, for every packet that it wants to send to this particular address, it has 2 possible ways. One of them is this /24, right? Because this contains this address. And one of them is this /32, which is exactly this address. Okay? So what is it going to do? Some of you have probably heard of longest prefix match routing, probably all of you. And so it's going to pick the longest prefix. What's the longest prefix? /32. Okay? So this is the classic prefix hijack. And we've seen this happen multiple times. It actually happened on April 3rd, just before I came here. Turkey did this. A network, sorry, not Turkey. It was in Indonesia, Indosat. Yeah. Yeah, they do block the /32. Yeah, so that's a max prefix length filter. There is a filter that will block this. So if you're running your routers properly, no, that's true. Most autonomous systems don't. So I'm just showing this attack because when I made these slides, this was like the day before the talk. But there have been many other different attacks. So you can imagine if this was a /22 and this was a /24, then it would win. I'm just showing this actually did work because this particular network wasn't filtering /32. Okay. Right, so to your question, yeah, the reason I showed this is because we know this was an attack. So here we have the attacker taking credit for it. So this is one of the few cases where we know it's an attack. But now I have here a slide full of different other attacks. So there's a famous Pakistan YouTube attack that people might have heard of. That was a /22 hijacking a /24. This was in China in 2010. That was a big deal in the US. This is some evidence that says it's being done for censorship in China. It's been done by the US as well, by networks in the US, so Con Ed did it. Some of you have probably heard of this. This was a big deal that traffic was going through Belarus and Iceland. This is again a prefix hijack. And then this happened last week. Indosat did one of these attacks. Okay, so these kinds of things are happening. And we're going to solve the problem with crypto. Okay, so actually, if you look at the solutions, I'm not here to tell you about solutions. I'm here to tell you about all the issues that take you to the point of actually getting these solutions deployed. Because the solutions themselves, you could probably think of them on your own, and we can construct them together as I go through the talk. So here are the two solutions. I said that this talk is about step 1 and step 2. This is step 1. Step 1 is the RPKI, the Resource Public Key Infrastructure. So this is a public key infrastructure for routing with some special properties. And this is already being deployed. And this is BGPSEC. BGPSEC is a cryptographic modification to BGP. Okay, so what's the difference between these two solutions? First of all, this one's being deployed. This one is being standardized. So this has not been built into any networks. This has actually it's about 10% deployment right now of the first solution here. So what does this thing do? This is an out-of-band mechanism. I'm going to tell you about the details of this. But basically, this is an out-of-band mechanism that routers can download information from and use it to check their routing announcements. So this is not any modification to the protocol I showed you. This is out-of-band information that's being used through a public key infrastructure. The second solution is an actual modification to the routing messages. So this is exactly what you would think of if you had done a course in crypto. You would say, let's sign all the routing messages so that people know what people are saying, and that's exactly what this solution is. Okay? Now, I'll show you exactly the details of what they do, but the questions that I'm most interested in, and that's where we are today with some partial RPKI deployment. So the questions that I'm interested in are really, how do you get these things deployed? And the real challenges that come into play is that you have a working system. It's the global internet. It's interdomain routing. You can't just turn it off and turn it back on again with a new, nice crypto protocol. You need to actually find some way to deploy this. And if you know anything about DNSSEC, we've seen that this takes a long time. Right? So we want to understand what happens on the road to deployment. And so we asked in particular 2 questions. This is the question in the first paper. What does BGPSEC offer over the RPKI? Now, when I show you this, it's going to seem obvious that BGPSEC offers something over the RPKI, but what we're going to show is actually the RPKI is doing more than people thought. And then the second question I'm going to look at is, what are the deployment challenges? And this in particular, I'm going to focus on RPKI deployment challenges. Okay, so now I need to tell you what these systems actually are, and of course, if you have questions, you should stop me. Okay, so I haven't actually explained to you how these work, but now let's look at how these work. Okay, so here's our attack. This is a classic subprefix hijack. We're going to be using it for the rest of the talk. So we have a /24 and a /32. Now, what does the RPKI do? We can think of it basically as an offline database. Okay, and the offline database contains cryptographic objects called ROAs, route origin authorization, as you can see very clearly on the slide. So what does this object have? Basically, it's a mapping between a prefix and an AS that's allowed to originate it. Okay, so what that means is that the first hop on any path, any BGP path for this prefix should be this AS. Okay, so that means, for example, in this particular case, what we would have is that this announcement here would be RPKI valid because this first hop and this prefix match this ROA. Right, so there's a matching ROA for this announcement. Whereas for this announcement, there's no matching ROA because this address doesn't actually belong to this network here. And by the way, you notice this is an interesting path, right? There are 3 networks here. These 2 no longer exist. You can no longer see these in the internet, so not sure what they were. Okay, so this is going to be RPKI valid. This one will be RPKI invalid. And so if our network over here is dropping RPKI invalid routes, which sounds really simple, but actually it's really complicated, but let's suppose he does this, then the attack is stopped. Okay, so that's what RPKI does. Okay. So you can look at this now. There we go. I was waiting for that. Okay, so how many people saw exactly what Danny saw? Next attack. Next slide. So this is why we need BGPSEC. Okay, so RPKI only does this. It does not do what Danny wants it to do. What does Danny want it to do? There we go. Right? RPKI valid, RPKI invalid. They're both valid. And so yeah, so what should our guy do? So actually, what do these networks do? They have to make some sort of routing decision. They have 2 prefixes, 2 different paths. So in this particular case, this path is long and this path is short. And so he's going to go for the short path and the attacker will win. Okay, so that's why we need BGPSEC. Now, I want to call your attention to one point. If we think about the /32 attack, the attacker was winning 100% of the time. right? Because longest prefix match always works. The first thing you do is you check for longest prefix match, which means in the previous attack that we looked at, the attacker was going to attract traffic from the entire network because it was a longer prefix. In this attack, these two prefixes are equal. And so that means he's only going to attract traffic from the people that he's closer to. And in this particular case, for example, he's not closer to this guy or that guy, and I don't think he's closer to that one either. Okay, so what's happening here is that by forcing the attacker to announce prefixes of equal length, right, then his power goes down. Okay, and so actually the RPKI is doing sort of more than you expect. So even though you can circumvent it for some networks, you can no longer circumvent it for all networks, as you could do before. Okay, so now let's see how BGPSEC works. Any guesses on how it works? So now what you do is you augment this PKI with keys, right? So you have a mapping from keys to autonomous systems, and you can now use these to sign routes. So this builds on RPKI because you still need to certify the mapping from the prefix to the autonomous system through Aroa, but now you also have the signatures on the routes, right? So now, Dunny, your attack will fail. Why is it going to fail? Right. So, but why? Why exactly? There's something particular about the structure. This is just for fun for me. I want to see. Right. So if the announcements were like this, Dunny's attack would still succeed, right? But what my notation is doing is that this guy is announcing to the neighbor that he's willing to accept traffic from. SCNet here is the path that you can use, and this whole blob is signed over here. So now if you wanted to do your attack, then what he would need to do is he would need to actually have this kind of message authorizing a link over here, right, which it doesn't exist, and so the attack fails. Okay, so that's how BGPSEC works. Basically, you sign on the forward link that you're sending the traffic out on.
You authenticate each link.
Yeah, you authenticate each link, exactly. Okay, so that's nice.
By
so
the way,
that's
this feature, it's not only a bug, it's also a feature. That Anycast servers with the same IP address from different locations in the world, and they use this.
Yeah, so this actually has.
Distance, so they need to authenticate all of them.
Yeah, actually, Anycast is not a problem for this because if you wanted to do.
You just authenticate all of them.
So if for Anycast, I guess if you were doing it with multiple ASs, you would have multiple ROAs, and that's allowed. So you should think of these ROAs as a whitelist. This is the list of ASs that are allowed to announce this prefix. The RPKI is designed so you can have as many as you want. Okay, yeah. Okay, good. So that's the setting. So now what we want to do is understand how much more we get from BGPSEC. I want to call your attention to another point. Note that this protocol actually involves signing announcements with public keys. So this is online public key crypto being done on every routing announcement. This is very different from downloading a ROA, which is a signed object, verifying it once, building up a table of ROAs that you've seen, right, and just using them to check against. So this is basically a whitelisting technology, and this is an online cryptographic solution, which is much more expensive. So we want to understand what's the gain. Okay, so in particular, what are we interested in? We wanted to study in this paper the partial deployment scenario. So what does partial deployment mean? What we want to do is we want to imagine is what happens when we get from an RPKI deployment all the way up to a BGPSEC deployment. Okay, so since we want to learn what BGPSEC does over RPKI, or the question we want to understand is as more and more networks deploy BGPSEC, what does it buy you in terms of security? Okay, so so to do this, we assumed a very specific setting. We assumed that RPKI was fully deployed, which means every network in the internet is using RPKI properly. Okay, in the way that I showed you in the first slide, which I see your eyebrows going up, that's a big deal, and my second paper is about that, but let's assume that that's being done. So if this is being done, all subprefix hijacks are eliminated. Similarly, all prefix hijacks are eliminated. The only attack that we have is the attack that you suggested, which is the one-hop hijack, right? So we have this attack here, this one, right, where the attacker claims to be connected to the legitimate origin. Okay, so the only attack we're going to worry about for the rest of the talk is this particular attack because we're assuming that RPKI has removed the more damaging attacks that we talked about before. Okay, so this is the attack that we're worried about. And now we want to understand what happens as more and more networks deploy BGPSEC. Okay, so we're going to think of a graph where some networks are active, have BGPSEC, and other networks are inactive, don't have BGPSEC, and see what happens in terms of preventing attacks. Okay, that's what this paper is about. All right, let's understand why that matters. So BGPSEC and partial deployment, what we need to think about in this setting is we need, in a partial deployment scenario, if you speak BGPSEC, you also have to speak plain BGP, because if you didn't, you'd lose access to the part of the internet that speaks BGP, right? And you wouldn't be able to route, so that would be horrible. So naturally, you need to accept, if you are a router that has BGPSEC, you also need to accept plain BGP announcements. Otherwise, you can't communicate. Okay, So now we can use this as an attack vector. In particular, we have protocol downgrade attacks, right? So let's look in particular at this scenario. Let's imagine that this is our network where the yellow nodes have BGPSEC and the purple node does not. Okay, so imagine it has just not upgraded yet. It doesn't have BGPSEC enabled routers. Let's imagine that this network was actually to launch an attack against us using plain BGP. So what I'm showing here is that this network here is learning a BGPSEC announcement on this path and a BGP announcement on this one. Okay, insecure, insecure. And again, this path is RPKI valid. Okay, so what should this router do? Okay, so it seems obvious that he should choose the secure route, but actually in practice this might not be true, and this is where the whole hook of this paper comes in, right? If you were running a network, you might not be willing to choose a 4-hop long secure path if you have a 1-hop insecure one that's shorter, right? If you're actually operating a network in this partial deployment scenario, you might not do that. And in particular, if you were to choose this short route, then you would actually choose the insecure route and be attacked. So that would be a protocol downgrade attack. Okay? So
you always insisted that if you have a choice between secure and insecure, you take the secure one even if it's long.
good, okay. That's exactly what we study. So let's try to understand what you gain or lose depending on how you prioritize security, okay? So that's what we did. We tried to study all these different models of how you could prioritize security. So here's the model that Adi mentioned. You prefer security over all other considerations. So here are the other considerations. So what are the other considerations used in BGP? So the first one is local preference. So what this essentially comes down to is cost. How much do you pay for a particular edge? Is this a provider network? Is this a customer network that pays you? So all of these kinds of considerations are the first priority, economic considerations. Then the second priority is exactly length, right? So how many hops on this path? Then there's a bunch more other priorities that we didn't model in this paper, okay? So anyway, these are the priorities that you have, and we tried to consider all of these different ones. So in the security first model, sort of everything works properly. This is kind of the gold standard, right? You prefer security over all else. This is kind of an interesting model, though, when you say that cost is somehow more important than security. And all the attacks so far that I've shown you have been path shortening attacks. Right? So here you will actually prefer a longer route if it's secure, as long as it's not more expensive. Okay, so that's what this model says. This is sort of the most iffy model. It's not really clear what's going to happen in this model. And in this model, you're going to prefer path length over security. And in fact, these are realistic models. We ran a survey on Nanog. We got 100 responses, which we were very excited about. And these are the sort of divisions. 10% told us that they would run security first. 20% security second, and the remaining said they would put it after path length. Okay, so all of these models, it's not really clear what operators would do in practice. And so it's sort of interesting to figure out that if they were using one of these models, how much of the attacks would actually be prevented.
Is there anything that characterizes the 10% with security first?
I don't know. I should check. I don't know. I don't remember. There was a... Yeah, no, I don't know. I don't know. I'm not sure. I think it might be like their level of involvement with these sorts of efforts potentially. I'm not really sure. Okay. So here's the research question now. So if everybody uses the same security model, so first of all, if they don't use the same security model, we can show instabilities and all kinds of bad stuff that we showed in the paper that I'm not going to talk about. So let's suppose that they use the same security model. If they use the same security model, what are the benefits of deploying BGPSEC at a set of SASs? Okay, so how many ASs do we need to deploy at before we get some kind of security benefits? Okay, now this is obviously going to be a difficult question if you're going to try this over all possible sets. Okay. And so we're not going to do that. We're going to skip over all that. So this is like sort of the technical insight that I'm going to show you what comes up next. What we're going to try to do is we're going to try to understand what are the benefits of these different security models independent of the set of ASs that you actually deploy the security model at. Okay. And in case you're wondering what this model was, it's the Gower-Rexford conditions, and I'll talk about it later if you're curious about that. Okay, so here's the insight. So what we want to do, we want to quantify security using only topology and routing policies. So let's look at this network here. Here's our attacker doing his one-hop attack. And let's look at what happens at green host. So let's suppose we're in the security third model. The security third model, route length is always more important than security. Okay, so in this particular model, green host will choose the attacked path because it's shorter. It's always shorter, right? If I undeploy, if I assume that nobody here is secure, right? He's also going to choose the attack path. If everyone's secure, he chooses the attack path. If no one's secure, he chooses the attack path, right? This path is always shorter. It doesn't matter what the deployment looks like. Okay? So what that means is we call this node doomed. This node is doomed independent of who has deployed BGPSEC. If this is the attacker and this is the victim, he's always going to go for the attack. Okay? We have a different class of nodes, which are called immune. If we look at these nodes here, if no one is secure in this network, this guy is always closer to here than he is to this. And similarly, this guy is always closer to here than he is to this, right? And since we're in the security third model, it actually doesn't matter at all whether BGPSEC is deployed or not. These nodes will always choose the insecure route. They always choose the legitimate route. So BGPSEC is actually not doing anything for anyone in this picture, except for that one node in the middle who has equal length paths. And if he's secure, let's suppose he chooses the secure route, because this is the security third model, and path length is more important than security. But otherwise, you go for security. And if there's no deployment, it's possible that he might switch to the other route. We don't really know. Okay? All right, so that's the point. The point is that there's only, in these different models, there's only a very small number of nodes that can actually be protected by the security deployment. Okay, so let's look at what this means. What we did was, this is security first model, second model, and third model. And what did we compute? We computed the average number of ASs that choose legitimate routes. Okay, so what we did was we started choosing attacker and destination and seeing what happened in the attack. How does traffic split during the attack? What this line here shows you, this shows you the line of the set of nodes that are immune. Okay? These are the set of nodes that would always go to the legitimate route, even if no BGPSEC was used at all. This is basically what the RPKI is doing for you. So I showed you those immune nodes, that's this part. Okay? Now the question is, what is the best you can do? So to figure out the best you can do, all you have to do is get rid of the doomed nodes. So for a given attacker and destination, independent of who's actually deployed security, right, you have this class of doomed nodes. You just count those doomed nodes and you subtract them out. And that gives you the nodes that will never be able to withstand these attacks, even with BGPSEC, for a given security model. And you can see sort of the improvement. So what you're seeing here in the security third model, you get a 17% improvement over what you get with just straight RPKI. Okay, so the security third model is not really offering you a lot of benefits. And remember that this is even with 100% deployment. Okay, it's just because you're using this routing policy. Whereas if you use security first, that you can get up to all of the attacks being stopped. Okay, so now just briefly, I want to show you. We tried this for many different scenarios, and we find actually that the picture looks even worse. So if 50% of the AS graph is secure, then in the security third model, we only get an improvement of 4% when we use this security third. So if path length is more important than security, even if you deploy half of the internet, it's not really going to do much for you. You might as well just use RPKI. In the security second model, it's kind of behaving a lot like the security third model, in particular for these kinds of partial deployments. And only when we get into the security first model, which is you prefer security over all else, you actually get these big gains. Okay, so that's roughly the point of the paper. And you might wonder how we did this. So we did this by simulations over AS level topologies, and I can talk about all the different robustness tests that we did, but I won't do that now. How much time do I have? 5. Okay, so can I show you the next piece? Let me show you very quickly the next piece. Okay, so this paper really shows you that RPKI can do a lot for you, I think. And now what we did was, and what we've been doing recently, what we've been most focusing on in my group is understanding RPKI deployment. Okay, so in the previous work, we just assumed 100% perfect RPKI deployment everywhere, and the question is, how can we get there? So there are lots of different issues. I want to focus on one particular issue, and this issue that I want to focus on is manipulation by nation states and abuse of authorities. So what happens if one of the authorities that are used in this system misbehaves? So I haven't told you what the authorities are, so I should probably do that. Okay, so I haven't told you how RPKI works. This is how it works. First, I'm going to talk about IP address allocation in the internet. This is a regional internet registry. It's ARIN. This is the American Registry of Internet Numbers. In Israel, I think you go through RIPE. It's a different one, the European. Now, what this is going to do, it allocates IP addresses to different organizations. So this IP prefix, right, a /12, this is a big prefix, goes to Sprint, and then it can get further suballocated to other organizations. Okay, so this is basically how IP address allocation works. Now, what does the RPKI do? It awards certificates. So if you have an IP prefix, now you're also going to get a cryptographic certificate. This is just an X509 certificate that has your IP address, and it's going to also have a key. And so then you will be able to sign a certificate for your sub-allocation that has that allocation, and they also have a key. Right? So now you have this certificate infrastructure in the obvious way, and the validity of the certificate depends on being covered by the parent. Right? So this is a subset of this, and so everything's okay. All right, so those are called resource certificates. And then I told you before about ROAs. So a ROA is a mapping from an IP prefix to an AS, and these RCs are used to issue ROAs, individual mappings. Okay, so that's the scenario. And finally, I told you that this was an offline protocol, so how do they actually deliver these certificates? All the objects issued by Sprint are going to be hosted in Sprint's publication point, so this is some sort of repository somewhere on the internet, and when you receive this certificate, it contains a pointer to the publication point, and then you just download everything in the publication point. Okay? So that means Sprint basically maintains control of every object that it issues. All right? So this is very interesting because today in the internet, there's no way to revoke IP addresses. If you allocate an IP address to someone, basically if they walk off with it, it's really hard to get it back. You might be able to do some sort of out-of-band mechanism, but there's no technical mechanism for you to recover an IP address. And once you start to use certificates, that becomes possible. So for example, and why does this matter? Well, first of all, we know of takedowns happening all the time in DNS. Right? So this is a document from ICANN explaining to people how to do a DNS takedown. So this is actually happening in DNS. And in fact, there have been requests to do IP address takedowns. There was this, and there was also a sex.com case in 2006. In both cases, they said we can't do IP address takedowns. There's no mechanism for this. Okay? But if you were to put this, right, so they actually demanded that RIPE do this, and RIPE said we have no technical mechanism, and that's how they got out of it. Okay, but now you can think about when we have certificates, we have certificate revocation lists, and we can do revocations. So in particular, if Sprint wanted to prevent this IP prefix from being announced by this autonomous system, what it could do is it could revoke the certificate that it issued to Continental Broadband, right? And then all of the stuff that it issued becomes invalid by default, and this thing will be revoked. Okay? All right. And of course, he can do this because there's just a certificate revocation list associated with this. Now, what we did in this paper that I'm not going to spend too much time on is we talked about various ways you could do this in a very sneaky way as opposed to just in a very public way with a certificate revocation list. One of the ways you can do this is, for example, to make it very targeted. So there's an interesting property of these certificates that they certify sets. This is a set rather than a name. Most PKIs usually certify names. This one certifies sets. So if I wanted to, for example, kill this particular grandchild, if this guy wanted to revoke this particular grandchild, all he has to do is remove the set that is contained in here, and this will become invalid while everything else becomes valid. Right? So you can do sort of these very targeted revocations, and what I demonstrated here, this overwriting, is also a feature of this system. You can overwrite certificates with new certificates. That's the way you deliver things.
All the papers published on broadcast revocation techniques.
Right.
We want to broadcast to a particular subset, to the paper with Moni wrote.
Actually, I need to talk to you guys more about these things. But we were actually trying to prevent revocations. Our concern was that this revocation mechanism would be abused and there would start to be this way of doing takedowns that would be too easy for people. And so what I want to talk to you about is, so this is sort of one thing that we showed. We discussed all these different ways of doing takedowns here that I'm not going to show you. And then another issue that's interesting with IP addresses that we similarly have in DNS, this is an international system. So for example, this is a network in Colombia. This is the American Registry of Internet Address. This does not have anything to do with Colombia, and yet it's a sub-allocation of Sprint. So this is sort of an international thing. And I'm going to skip the slide that shows you how international it is, but you can believe me that it is. This is sort of interesting. This address, this /8 is used in all these different countries here, and this /8, which is a huge space, is used in all these different countries here. So you can see that this is creating some interesting issues, jurisdictional issues in the internet. Okay, so we did a lot of work on that, and now I just wanted to show you something that we submitted a couple of months ago. This is the first time I'm talking about it in public. What we were trying to do is we want to propose a modification to the RPKI, which is still possible because there's still standards being made on the RPKI. And our modification is to make revocation more difficult in one way. What we're really trying to do is we're trying to distinguish between a revocation that's done with the consent of all the parties involved, like for example, I'm giving up my space because our contract is over, versus a revocation that's done as part of a dispute or as part of potentially international issues or anything like that. So how can we distinguish between a revocation that was agreed upon and to a revocation that was not agreed upon? Right now we cannot do that. So what we want to do is we want to build a mechanism that allows you to do that. So our mechanism has two pieces. The first one is consent. So what this mechanism wants to do is it wants to allow people to consent to their own revocation. Okay, so here's how you do it. We introduce this new object. Instead of certificate revocation lists, we have these revocation objects. We call them .dead objects. And what you do is if this guy is consenting to be revoked, what he's going to do is he's going to sign on his .dead. Right? This guy has a key because he's a certificate. Right? He signs on his .dead, and then all of the children will sign on the .det as well, right? So you start to collect signatures sort of from the subtree that's being revoked. The parent will sign it, and then you can see that everyone here has agreed to be revoked. Okay, so really what we're trying to do here is we're trying to eliminate unilateral revocations. We're trying to do sort of a bilateral revocation. So again, this sort of revocation issue is, sometimes people think about solving it by distributing the certificate authorities. What we're trying to do is actually not distribute the certificate authorities. The issuance should still be easy. The issuance of certificates should be easy, but this really uncommon case of revocation should be more difficult. Okay, so we did a whole bunch of thinking about that. And the second piece that we added to this proposal was to make it more transparent. I'm not going to talk about any of this. I guess to say one word about it, what we're trying to do is keep a log of what's been issued by a particular authority so that we can make sure that he's showing consistent views to the entire world, not sort of showing you one thing, showing me another. And also that you can tell what certificates used to be issued here and what weren't and what have been revoked. Okay, so this is something that we've been working on. I don't know if I presented it very well, but anyway, that was the first time. Okay, so to summarize, what I think is interesting and important right now is RPKI is in this early deployment stage. There is an opportunity to actually sort of change the standard or to improve it, so that's kind of where we are right now. And this sort of first work that I showed you, I think, suggests that the gains that you can do that are actually quite high, and so putting the effort into RPKI right now seems like the right thing to do. Okay, and that's it. Thank you.